So I call this thinking inside a box. First of all, how many of you use Linux? Oh, great. Okay, so this may actually be applicable to you. The feature I'm going to talk about today is very specific to Linux. It's not available on most other desktop operating systems or mobile operating systems that I know of. However, it's really not an end in itself, it's a path. So even if this doesn't seem like it directly applies to you, I believe it may help us get where we all want to be. So data flow is a pretty old concept. It's nothing that novel anymore, but basically the idea is you have nodes that do processing and they receive data as inputs and they produce data as output, and the data can be either single units of atomic pieces of information like an integer or a float or something like that. An example of that would be like Faust, or they can be streams of data. And what I'm going to focus on today is the streaming version of data flow. A key point is that within each node, it should be a pure computation. And I'm using pure in the sense not of pure data, but of pure as in functional, meaning it has inputs, it produces outputs, but it has no global effect and is not affected by the outside world. It may have private state. I will allow that. And I'm also going to restrict myself for today to data that's plain old data. And by plain old data or pod data, I mean integers, floats, enums, booleans, and then conglomerations of those. So arrays of other plain old data, structures, things like that, but no references or objects. And the reason for that is that if you have plain old data flowing through a stream, it's very easy to copy it safely and without ever worrying about losing it. So let's see what happens if we run data flow on top of Linux. Okay, I'll take this data flow graph, run it on top of the Linux kernel, and delve a little bit deeper into that. So we basically have a very, very simple application. It's these real-time audio tasks that are communicating with each other via plain old data, and they're all functional in nature. They're not making any system calls. And we're running it on top of this huge Linux kernel. I mean, the Linux kernel is like, I don't know, millions of lines of code now, horrendously complex, full of bugs, full of performance bugs especially, and it's running on the CPU, which is very, very powerful, but totally unpredictable. Not totally, but for our purposes, for audio purposes, it's unpredictable. So we have a real mismatch in architecture. This is not a good way to run data flow, in my opinion. Somebody else here earlier, I put out the question, what would be a better operating system? You said no operating system. Yeah, that's certainly fine. Or perhaps a real-time operating system. That's pretty darn close to being to no operating system. And we can have the same architecture, run it on an RTOS, and instead of running on a traditional application processor, which has this unpredictable performance, let's run it on a microcontroller or DSP or something like the Bella project, which is, it's an application processor, but it's been tweaked to give more consistent performance. And the key thing, though, is that our RTOS or bare operating system has to have inter-process communication, because we still need the rest of our application. We still need the GUI and everything related to that. We still need USB, etc. These two worlds have to talk to each other over either over shared memory or some sort of high-speed serial bus. I believe in the Bella case, they did use shared memory. How much more time do I have?
18 minutes.
18, okay, great, okay. So this is where I think we need to be, but it's a huge switch. I mean, I thought Bella was beautiful. I think it's a great project. Getting there, though, is the hard part. I mean, considering we're at least on Android where we are now, to jump from there to Bella is a big change. It's a big change for application programmers. It's a big change for operating system developers. It's a big change for the SoC vendors. So I want to propose today a path for how to get to systems like Bella via an intermediate step. This is definitely work in progress. This is not a product-oriented talk, so I don't want anybody going back and telling my manager that Glenn claimed that Google was working on this or was going to deliver something like this. This is definitely just an experiment and could totally turn out to not work at all. So that's the reason I'm showing it to you early, is because I want to get your feedback on it. What I've described is again, not a new concept. It's called heterogeneous computing. In fact, I was at the ARM technical conference last week, and they had a paper on this very subject of having two different kinds of CPU architecture on the same chip. In that case, they had a Cortex-A and a Cortex-M. The reason why it's become more popular again now is because it's much cheaper now. You can actually put them on the same die, and we're seeing the performance problems of trying to run everything on a massive processor like an A series. So I said that I think we can get there via an intermediate step, and the intermediate step is something called a secure sandbox. So many of you said that you are familiar with Linux. By show of hands, those who are familiar with user versus kernel mode? Okay, about half of you. So I'll try to go through this, but fairly quick so that we have time to get to the key point. So CPUs have at least two modes. Often they have more than that, but they have a user mode, which is the upper part, and the kernel mode, which I'll show in the lower part. And it's also called privileged mode and unprivileged mode, something like that. The kernel obviously runs in kernel mode, and then your applications run in the user mode. And the way you transition between them is primarily via a system call. For example, if you do the open system call or the read system call or write, that results in a transition from user mode into kernel mode, and then when the kernel is done, you go back. There are other transitions possible too, such as interrupts and exceptions, but we're going to skip over those. We're just going to focus on the system calls today. Now, if you look at that system call in more detail, it turns out it's a really thin layer. You simply load up the registers with certain magic numbers, and then you execute a special instruction. You go off to the kernel, it does its work, and then you come back and you have a result in one of the registers. The interesting thing to me about this is that it's such a thin layer. It's not a very complex interface. You have registers coming in, a special instruction, and then registers coming out. It's a very clear boundary, and it's a very convenient place to interpose something. And what we're going to interpose is a semipermeable membrane. So a semipermeable membrane allows certain things through, but doesn't allow other things through. So in this case, we're going to allow the purple circles and the oblong purple things through, but not the X's or the red checks. And these represent system calls. So we're going to allow certain system calls to be executed, and we're going to deny other system calls. This is called secure computation, or seccomp. And it basically answers the question, which system calls are permitted to pass through this membrane? By default, all system calls are permitted. So you have the full power of this large and complex Linux available to you. But you can restrict it using seccomp. During Jules's talk, he mentioned about domain-specific languages and byte codes and things like that. Seccomp is a domain-specific language, and it's implemented using byte codes. I'll show you the language in just a moment, but basically the end result of a seccomp program is a decision. And the decision is, do we allow this system call to be executed or not? And if not, what's the error handling? So green indicates that the system call is allowed to pass through into the kernel. The yellow and the red mean either you can force an error code to be returned or you can just simply kill the process. We don't use the black options. So here's don't worry, we're not going to go through this in detail, but here's a very simple, relatively speaking, setcomp filter or bytecode program. And I'll show you what it does on the next slide. But the summary is this allows 2 system calls to be executed and no other ones. And the 2 system calls are called futex wait and futex wake up. You can think of those as equivalent to semaphores or mutexes. They're basically ways of sleeping and waking up. And everything else causes the application to either die immediately or at least to return an error code. We can represent that bytecode or that program as a graph. What happens is it looks at the register containing the system call number, checks whether it's the futex system call. If so, it does a few more checks to see whether it's wait or wake up. And if not, it just simply kills the process. And then for the purposes of the demo I'm going to show you, we're also going to allow the write system call to be executed, except we're going to return a particular error code. So why did I pick futex and why only futex? It turns out that's sufficient to implement dataflow. So now we can run a simple dataflow computation on top of Linux and yet not be reliant on the rest of Linux. We're only reliant on the wait and wake up. This green node, I'll go back here, what it does is it's a thread. It waits for its inputs to become available. Then it does a computation. Then it does a wake up, which will place its result in shared memory, and then those outputs can be available to another thread. So I was going to give a live demo at this point, but it didn't quite work out. So instead, I'm going to give a pre-recorded demo. Instead of a whole graph here, I'm just going to show a single node that's going to do a pure computation. It's going to receive its inputs via shared memory, but a special kind of shared memory data structure, which is we're going to learn more about in Timur's talk, which is the lock-free queue, also known as the circular buffer. 2 different implementations of the same concept. And it'll put its outputs also into a lock-free queue or circular buffer in shared memory. And it's running within this secure computation sandbox. So the only thing it can do is the pure computation and nothing else. All it can do is wait for the data to be available as input, do its computation, and then signal that it has done its part. So this is not the full this is not the full code, but it's showing the important part of the pure computation. So I have a function which computes the cube of an integer, and in most cases, in the default case, it just simply returns the cube. However, in a few special cases, it's going to do something different. In one case, it'll execute the read system call, which is forbidden. In case of 8, it'll do the write system call, which is also forbidden, but instead of killing the process, will return an error code, which we can look at in Erno. And in the case of a 9, it's going to go into an infinite loop, okay, which is a bad thing. So the pre-recorded demo is you. All right, if I give as input the number 3, what's the output here?
27.
Exactly, 27. And if I give, let's say 8, what do we get? Some error code, some random error code. If we get 7, that thread is going to die instantly, all right? But the parent process can detect it and recover from it, so it doesn't kill the whole system. And then finally, in the case of 9, it goes into an infinite loop. But again, what can the parent process do? It can detect it and recover from it. And because this is a pure computation, and the only memory it has access to is its inputs and its outputs, which can be placed in protected memory, it turns out we can safely allow all of these options to occur, and we can recover from them. So I'm going to skip over this part because we don't really have time for it, and it's not necessary. But if you've heard of SE Linux, this is not SE Linux, it's something else. Why does this matter? I mean, why would you want to do this? The main benefit is sure, you could load untrusted code, let's say a DSP plugin that you've purchased on a store. This would allow you to run it in a safe sandbox. But that's not the main point. The main point is it provides us a path to where I feel like we actually need to go, which is running real-time audio code on either a microcontroller or a DSP or some sort of an A-series processor that's been configured for real-time, such as the Bella project. But in a constrained environment where we can debug it, we can test it in this dataflow sandbox, and then deploy it for real in the target environment. It seems like a terribly constrained environment. One of the things I really liked about Jules's talk earlier today is he talked about constraints, and he had quite a few of them. I guess there were 10 of them, I think. So this is a massive constraint. If you're used to working on Linux, this is a huge constraint to no longer be able to issue any system calls. But within constraints comes creativity. I was searching online for a great example of creativity and constraints, and I found this one. I'm sure it's very old and hackneyed, and some of you have seen it before, but for me, it was new, and it actually brought a tear to my eyes. And the constraint this writer had was that they had to write a short story in 6 words. And I think that they did a great job of coming up with something really powerful. I think the same thing can happen here with dataflow, which is, it's a very tight environment. It requires a new way of coding, a new way of thinking. But within that environment, I think it opens up a world of opportunity. And I believe it'll allow us to eventually move to a new architecture where we run our real-time audio computations in an environment that's actually appropriate for that, rather than an over-designed CPU and an over-designed kernel. So that's my talk. Thank you for coming.